Hi, everyone. Thanks so much for coming today. We have a special guest, Gary Solon, and for health concerns, he is here in person, and we're absolutely delighted to have him here in person. But we wanted to ask if you don't mind masking to help protect Gary. Before we get started, I wanted to show you something else. We are trying to make it as easy as possible for everyone to remember when our seminar is and who is coming. So I wanted to show you, if you go to our website under events, current seminars, I guess I can see it better on the screen over here. You can go, when you click on those events and seminars, you can actually subscribe to a calendar. And if you click on that, it will give you a number of options, including Google Calendar, Microsoft, any of those things. And you can kind of do this and download it, and you subscribe, it just pops up right in your calendar and you can see it, which I find extremely helpful. So in case that saves you creating all sorts of events on your calendar this year, you can do this. Let me see. So let me come back, and I wanted to say a few words about Gary before we get started. The first thing I should say is we have 2 or maybe 3 different programs running in this seminar time. You'll hear about these and it might be confusing. We have our seminars, we have our workshops, and then we have scientific and technical core workshops, and we have development workshops. They all are essentially at the same time. You don't need to know the distinction, but the distinction is that these workshops are aimed at sort of increasing or conveying information about new technical methods, methodological approaches to demography. And so we're going to be featuring a number of speakers this year. Gary Solon is our first of those speakers. So Gary is an old and dear friend of mine. I wanted to tell you a little bit about him before he gets started. The first is, so I'm going to kind of go through some history here.
This might be embarrassing.
Okay. No, I don't think it's embarrassing.
But I can handle it.
But Gary didn't start his career as an economist. He started it, I think, as a statistician, right? He got his statistics major at Harvard in 1975. He was a mathematical statistician working for the Census Bureau and then the US Department of Labor. And then he went back to get his PhD in economics at Princeton and joined the faculty at the University of Michigan in 1983, where he remained until 2007. And he hired me in 2005. So I was very pleased that he was there. So thank you, Gary. But I will say there's a number of things that I learned from Gary in our very short period of overlap. And I should say after the University of Michigan, he moved to Michigan State and then moved to Arizona. And now he's retired, but comes to hang out with friends and offer fantastic seminars like this anyway. So, and he just told me how much he missed hanging out with a bunch of academics. So maybe we'll convince him to come back out of retirement. So in Michigan, Gary did a couple of things that I, in retrospect, realize are kind of pathbreak and pioneering. One of the things that you told me, and I don't know the genesis of this term, was called terra firma economics. And what Gary meant by that was he really helped as part of his role, both in the labor group and also through department hiring, and also then as chair. He wanted to shape the department to be something that was not only grounded in theory, and at that point in time, economics was a very theoretical discipline, but also in testing those theories in the real world, or something that I call like in the wild. So in that same spirit, Gary also taught this course that I think shaped generations of students in applied econometrics, which wasn't just about the asymptotics, but was actually about, again, how to apply those things in the wild. Like, what do you do when faced with real world problems? For example, like this one, weights. What do you do about weights? So helpful. He taught a ton of courses, and that course was so popular that I know people from across the university, public health, sociology, political science, people came in droves to take this class, and assistant professors who joined, who'd already had a lot of econometrics, like me, also sat through Gary's class because it was so fantastic and just so grounded in like all of the things you needed to know, connecting many different things. One of the things I'll say is, like, Gary's research has been pioneering for a very, very long time. In so many ways, and he has received a lot of distinctions, but in some of our views, not enough. But one of the things is, like, Gary was working on topics that are now really, really hot way before they were cool, like intergenerational mobility. Like, Gary is one of sort of the pioneers in this literature. And there's also, in addition to his many research contributions, I wanted to say that, like, Gary has just been a public servant extraordinaire. He reads papers. He's very careful. He always, he's been, I think he demands excellence of his students, but he also supports them and raises them up at every turn. And his list of advisees, I think, is probably longer than his CV, which is very, very long. But there's a whole lot of advisees. Some of them you may have heard of. He was able to identify and support talent like John DiNardo, who was an undergraduate of Gary's at the University of Michigan. But Michael Baker, Marianne Page, Stephen Hyder, and one of his last students at Michigan, Pat Klein, who I know all of you have heard of, just to name a few. That's just a handful, but there are many, many more. So beyond all of these things, he's always been an incredible mentor and friend to me. So with that, let me thank Gary for coming to see us, coming out of retirement to give us this great seminar, and I'll pass the floor over to you.
Great, thank you so much. Wow. Maybe we should just stop there. It's not going to get any better than that. I had a list of 4 preliminary remarks, but I also have one preliminary remark on the fly.
Should I get your slides up?
I think it does it just go forward from there? Oh, I see.
And then
here's some
buried under the there.
Okay, I just need to back it up to the first page. I probably wasn't pushing it hard. But what am I supposed to do? There.
How do you do the Dylan? Do you know how to get the?
All I need to know is how to move it up and down. I'll do it. Okay.
I can also add, Gary told me this morning that this paper is on its way to being one of his most cited.
Oh, that might be the room.
Almost there, even though it's one of his most recent. Okay, it works.
Great, thank you so much for everything. Okay, so the preliminary remark is simply I've been having a blast this morning, and I guess I hadn't realized how much I like talking to people about their dissertations. Maybe retirement wasn't that great of an idea. The first prepared preliminary remark, which I owe all the more now, is a big thank you to my longtime friend Martha, now for her wonderful praise at the beginning, but also for inviting me and hosting me. Secondly, a big thank you to all of you who are masking. I think Martha had explained earlier on my peculiar medical vulnerability, and I appreciate your doing this. I mean, we all hate wearing these masks. I hate it too, but anyway, I appreciate your doing it to help protect me. Third, I guess I will apologize in advance for my rustiness as a presenter. It's actually years since the last presentation I did in person. And because I retired 5 years ago, and this literally, because I retired before the pandemic, and didn't have the experience of pandemic teaching, this is literally the first time I'm ever presenting with a mask on. Didn't have to go through that. So it's likely that I'm going to screw up in various ways out of my rustiness. For example, please let me know if I'm not talking loud enough, given that I'm muffled by the mask, but that's just an example. It's all right so far. Anything else I screw up about, I actually would welcome getting coached to fix. Finally, I want to comment on the weirdness of presenting a paper that was published 8 years ago. This certainly has not been my common practice in my own career. Usually I would present a new paper because, first of all, I wanted to publicize it, and maybe even more than that, I wanted to get feedback to keep making the paper better. So that's not the agenda today so much. And it does raise the question of, why should I even be talking with you about a paper published 8 years ago when you can just go read it at your own convenience? And of course, I'd love you to read it at your own convenience. Read all of my papers, please, but including this one. What we get from doing a session like this is the possibility of interaction. If you read the paper and you have a question or a comment or whatever, I'm not there to engage with about it, although you could email me. But today I am here. So I very much want to encourage you to speak up with comments, questions, jokes, songs, insults, whatever. It's all fair game. Okay, so on with it. This is, I guess, my most mischievous title of a paper over my career. What are we waiting for? And it's a good title, not only because it sounds funny, but also because it's exactly on message for what the paper has to say, as you'll see. I did this work while I was at Michigan State, and it's co-written with Michigan State colleagues who are still there, Stephen Heider and Jeff Wooldridge. And also, if you do want to look up the paper, there's the citation, Journal of Human Resources, spring 2015. We begin the paper by quoting two top-notch practitioners, Josh Angrist and Steve Pishka, in their famous and useful econometrics textbook, Mostly Harmless Econometrics, where they confess to confusion and dismay on the subject of weighting. And I can tell you from my own conversations with leading researchers, some of them much more leading than I am, that Angrist and Pishka were not alone in this, that it's a lot of people were pretty confused about how to think about weighting. The central theme of our paper is that the confusion stems from a lack of clarity about which among multiple possible reasons to weight is the one that's on the table for the particular research project at hand. And our contention is that once one gets specific about why you're even thinking about reweighting your data, then it becomes a lot more straightforward to consider whether that purpose really does apply. In many cases, there are diagnostics you can do to double check your conjecture that it applies. Whoops, where did that come from? And then to proceed with a good choice about how to do your estimation and inference. Hence the title, What Are We Waiting For? Okay. The way we start that effort to pin down why are we even thinking about weighting is to ask the prior question of what is it we're trying to estimate anyway? And in this taxonomy, we specify two categories, which do seem to encompass most of the research that I and my friends do. The first type is studies designed to estimate descriptive statistics for a particular population. And actually, this morning I've been talking with people some about work on intergenerational income mobility, and at least the first few papers I wrote about that were descriptive in nature. You know, just what is the intergenerational association in socioeconomic status, which then pretty quickly leads to questions about, well, what are the underlying causal processes? But it starts off as descriptive work. How much intergenerational mobility or immobility is there? The other type is studies designed to identify causal effects, which probably most of us in the room have been engaging in a lot as well. We discussed the two types in turn. In the first type, it turns out the weighting issue is kind of trivially simple. It has been known to be so, at least by the survey statisticians, for many decades. So I'll go through that, but that's not what we'll spend most of our time on because it's so well understood that there's no need for a new paper about it. The need for the new paper had to do with the second type. And in the case of identifying causal effects, it's trickier, but we contend that it can be made straightforward by careful attention to which of several potential motives for weighting is what's getting you to think about doing the weighting. Okay? I'll start with the easy case. And since two of the co-authors, Stephen Heider and I, base so much of our work on the panel study of income dynamics, we'll do a PSID example. which is about what if we want to estimate the US poverty rate for 1967, which was actually the first year for which the PSID had income data. Now we know what the current population survey said was the poverty rate for the United States that year. The Census Bureau told us in their official poverty statistics, it was 13%. So the kind of stupid question that we proceed with for illustrative purposes is what if you made the mistake of estimating the poverty rate on the basis of the PSID in a naive way, not taking into account that the PSID deliberately oversampled the low-income population. And that wasn't a mistake that they did that. It was on purpose because a lot of the motivation for funding of the survey was to study poverty. So they needed a lot of poor people to study. So, you know, the poor sample would be big enough. Now, if you just estimated the poverty rate on the basis of the full PSID sample without any reweighting, and we did this, Stephen Heider actually did the computing, you get a US poverty rate of 26%, double the official rate. But 26% is a stupid estimate, to use a technical expression. Of course, the PSID, if you handle it that way, is going to overestimate the poverty rate because by design, the survey oversampled the poor. Absent some other problems with the PSID, which Shiva and I were talking about earlier, you could achieve unbiased and consistent estimation by using the PSID sample's weighted poverty rate, weighting by the inverse probabilities of selection. And that leads to a 12% estimate of the poverty rate, which is quite consistent with the official statistic from the Census Bureau. The visualization that I used through the paper for what this is about is that by design, the PSID sample processed the US population through a funhouse mirror that exaggerated the low income part of the population. But the reweighting, weighting by inverse probability the selection does is kind of do the inverse distortion so that you're back to getting a more accurate picture of the population. In the paper, we point out that this is a more general point, and we illustrate with a regression example about describing the black-white earnings gap between men with the same education and work experience. I don't think that it'd be very helpful to devote time in the seminar to going into the weeds on that. But it turns out, again, that you get different answers if you don't reweight the data, and then in that analysis, you're kind of over-representing the low-income part of the population than if you reweight to get a more accurate picture of the population. And what that's doing is illustrating that we're talking about a quite general point here. And I'll just summarize it here. And none of this is certainly would be news to any survey statisticians. So this is old news. The bottom line is when estimating a descriptive statistic for a population, estimating with the analogous sample statistic is consistent when the sample is representative of the target population. For example, if you had a well-executed simple random sample from the population, it's the simplest example. But if the sample is systematically unrepresentative, as with the PSID's oversampling of the poor, generally you aren't going to get consistent estimation of a population statistic with the analogous sample statistic. You get a 26% poverty rate instead of 12 or 13. But when the sample is unrepresentative in a known manner, the population statistic can be consistently estimated by reweighting the sample statistic by the inverse probabilities of selection. And my waving my hands about funhouse mirrors is not really a proof, but if you'd like to see the proof, here's the citation. My co-author Jeff Woolbridge has an excellent technical paper in Econometrica 99, which shows that this insight applies to the entire class of M estimation. And we aren't going to get into defining M estimation right now, except to say it's such a broad it's such a broad category that probably any estimator that any of us in this room ever uses will reside within that class. Yes.
You may not want to go into this now, but if you were to take a different year of the PSID when there were more new households that were split offs, would you still say it's kind of straightforward to think about how to rate it, since you have the intergenerational correlation of parent and child that refreshes basic example?
The further you get into, Shiva and I were talking about this a little bit, half an hour ago. The further you get into the PSID, the more troublesome it gets to do the correct reweighting. The PSID staff try to facilitate it. They provide weights, but here's the problem. Although the year-to-year attrition in the PSID is only a few percent, over the years it accumulates to a lot. And the truth, since I'm not on the PSID payroll, I guess I will say what I think is the truth, which is nobody has any idea what the PSID sample today really represents. Because the cumulative attrition is just endogenously decided by stuff like people just deciding, do they want to be in the survey anymore? And what the provided weights are doing is they're weighting in a way so that when you use the weights for a bunch of observable characteristics, I don't remember the whole list exactly, but it's very age, race, gender, the usual suspects, that it will match benchmarks from cross-sectional surveys like the current population survey. But we're still left with the question of, is the sample unrepresentative with respect to unobservables? And sort of by definition, we don't get to observe those. So it's things get a lot trickier the further the survey goes along because of the accumulation of sample selection that probably has endogenous aspects to it. And in my first full paper on intergenerational mobility, a referee who I suspected was Joe Altanji kind of forced me to add a discussion to that. And that's the kind of referee comment you want, because he was right, that needed to be in the paper. It made it a better paper. The position I took in that pretty much was, well, yeah, this probably isn't altogether random. Let me speculate about the likely direction of the bias that results from that. And that's often the best you can do. Okay, other questions or comments? Okay, so now we get to the heart. That was the easy part. Like the slide says, all of this is intuitive and not controversial. So where do the confusion and dismay come from? And that's because a large portion of the research that we do, I wrote the paper mainly for economists, but I think the lessons are applicable to sociology and public health and lots else. A lot of the work that we're all doing is about estimating causal effects. And in that type of research, the weighting issue becomes more nuanced. I find that people often want me to just say, yes, you should always weight, or no, you should never weight. And neither one is the right answer. The right answer is it depends. And what we're going to spend the rest of our time on is what it depends on. Okay? The way we organize this is we focus in turn on three distinct potential motives for weighting. And I should add something that we have in a footnote, which is these are not actually exhaustive. There are other reasons people weight data. But these are the ones that I think are most likely to come up for most of us practitioners in the room. So that's why we focus on these in particular. The first one goes way back to a previous century, back when I was taking my econometrics classes. Really the only time we talked about weighting in those was to achieve precise estimates by correcting for a heteroskedastic error term. And that is still sometimes a salient issue, and we'll look at an example of that. But it turns out people have basically overshot on that. It turns out the commonly used weighting strategy is probably overshooting in most cases. So we'll talk about that. The second, which is a very meritorious reason, is to achieve consistent estimates by correcting for endogenous sampling. This turns out to be a lot like the funhouse mirror story. And finally, a reason that turns out to be incorrect, but at least was commonly believed at the time we were writing the paper, was that reweighting would help you with identifying average partial effects in the presence of unmodeled heterogeneity of effects. So we'll be discussing that as well. And again, our contention is that clarity about whether and how to weight requires focusing on which motive, such as which of these three, is really on the table in your project, and thinking hard about whether it really applies, and applying appropriate diagnostics to double check. Okay? So now we'll just go through those in turn. Starting with the old-fashioned one of correcting for heteroskedasticity, which has been taught for decades in undergraduate and graduate econometrics classes. The idea is with the heteroskedastic error term, if you either know the nature of the heteroskedasticity or at least can estimate it well, you have an opportunity to achieve more precise estimation in a linear or nonlinear regression model by doing an optimal reweighting of the data. The applied example we go through in the paper is from my own research experience. It's in a literature about whether, and if so, how much, introducing unilateral divorce in the 1970s raised the divorce rate in the United States. I'm probably one of the only people in the room old enough to remember back when it was really hard to get a divorce, even if you fervently wanted it, or it could be hard, because under the old laws, the divorce had to be mutually agreed to by the two parties in the marriage. And of course, if somebody was looking for a divorce, they probably weren't getting along that well, and cooperating on that wasn't necessarily going to happen. I guess this was not actually a very popular situation with the citizenry, and eventually the state legislatures responded to that, largely in the 1970s, by rewriting their laws to make unilateral divorce possible. If one member of the relationship wanted out, it could be done. And to this day, of course, there's still all the stuff to work out about the terms, but the divorce could happen just because one of the two people wanted a divorce. So two American Economic Review papers, first by Leora Friedberg in '98, and then by Justin Wolfers in '06, did just the research design you would probably think of, for good reason, knowing that different states adopted unilateral divorce laws at different times. So they did a difference in differences type estimation of the impact on the divorce rates. They used a panel of annual state divorce rates over time, estimated linear regressions of the divorce rate on dummy variables to represent the presence of unilateral divorce laws, and controlled for state fixed effects, and in various ways controlled for secular time trends. And both Friedberg and Wolfers basically just, following her example, weighted their observations by the state year population in the estimation of their regression models. And Friedberg justified this as a correction for population size related heteroskedasticity in the state year error term. Now, I'm going to tell you why that might be a bad idea. But at the same time, I want to emphasize that this was very standard practice. In fact, we have a footnote that lists, like the best researchers in empirical micro, including Adriana, papers published in very top journals, that just as a matter of course, we're doing weighting like this. And it was just kind of thought to be the obvious right thing to do. The reason, I guess, the reason I started worrying about this was because of a paper by my fellow labor economist, Bill Dickens, which eventually was published in the Review of Economics and Statistics, which kind of changed my world on this subject with a very good insight. But I don't think the world was paying enough attention to his paper, even though it was in a pretty good journal, it was mostly overlooked. And actually the function of this paper, there's probably not a single new result in this paper of mine. It's a synthesis of what was out there, but a lot of what was out there was just not, just people weren't reading it. And if you look at the bibliography, you'll see there are a lot of Jeff Wooldridge papers. And usually when you see that, you think, oh, Jeff insisted on citing his own papers to the max, but actually it was my doing. I was familiar with those papers. I felt I'd learned a lot from them, but they're very technical papers, and it bothered me that practitioners weren't reading them. So that's another example of how this paper is really kind of regurgitating old results, but publicizing them to an audience that was probably less aware of them than we thought they should be. Now, what is this table? This is from a paper by a very good Michigan State student named Jin Young Lee and me that replicated and extended Wolfers's work, which in turn was replicating and extending Friedberg's. And first, let me just quickly describe the regressions. It's differences and differences. In this, there's a lot of stuff reported in our paper, and of course, I'd love you to read it. And the references in the paper at the end of this paper. But what we're doing here is regressing log of the divorce rate for state I in year T over the same, what was it, like 33-year span that Wolfers was using, and regressing those on following Wolfers a bunch of dummy variables about whether the state has unilateral divorce laws in place. Now, the big insight of Wolfers's paper, which is a really important one for fixed effects estimation in general, is his criticism of Friedberg, or let's say extension of it, was the effects of unilateral divorce laws on the divorce rate were not necessarily constant over time. The short run effects and the long run effects could be different. And I think the main thing he had in mind was that there was pent up demand for divorce, which would cause the early impact to be larger than the later impact. So he had the very good idea of, instead of having just one dummy variable for whether unilateral divorce was in effect, to create this whole set of them that's listed here. Has it been in effect for up to 2 years? Has it been in effect 3 to 4 years, and so forth, finally getting up to 15 plus. Now, there are a lot of interesting things to say about this topic, but there's really only one I want to emphasize for the purposes of this talk. And that is, remember, the point of doing weighted least squares instead of OLS was to improve precision, is the traditional heteroskedasticity motivation. But what we have in parentheses here are heteroskedasticity robust standard errors. So they're agnostic about what the heteroskedasticity actually is. Those are going to be consistent standard errors for either OLS or weighted least squares, regardless of what the true nature of the heteroskedasticity was. Now do the comparison between the two columns, and you see, even though the purpose of weighted least squares putatively was to improve precision, it actually did the opposite. The standard errors are bigger for weighted least squares, and for the short legs, they're dramatically bigger. And so this raises the question of what went wrong here? Or you might say, oh, well, maybe Jin Young and Gary made a computing mistake, but I don't think so. Let's talk about why this happens. Yeah?
A question there in the systems of the hypothesis that the only thing that errors are doing
What was changing?
The coefficients are changing very substantially, so it's not just standard errors that. But that would suggest something else.
They're both going. Well, Wolfers had a very good idea in thinking that the long run effects could be different from the short run effect. Between the two columns, you mean?
Yeah.
Yes, that also. In our Jin Yang's in my paper also talks about misspecification issues. And actually, in terms of error structure, we also note that a much bigger issue with these data than heteroskedasticity is actually serial correlation. So there's lots of stuff going on here. But for purposes of today's talk, or this part of today's talk, heteroskedasticity, I will get back to functional form misspecification a little bit later on with this example. But yeah, lots of stuff going on there. Okay, well, first of all, let's reconstruct what Leora Friedberg was thinking, and then talk about where she went wrong, along with, many, many other leading researchers. I'll simplify by taking the case of a cross-sectional regression to avoid the complication of having, the T subscript as well as the I subscript. So let's just say we're estimating a linear regression model of Y on an X vector, where Y sub I is a group level average outcome. In the case of this research, it's the state divorce rate, but it could be any group level average. And then the error term VIE is a group average of the error term, of the micro level error terms, as written there. It's the sum of the VIs in the state divided by the within state sample size, capital J sub I. Now, if the micro level V satisfied the ideal conditions with constant variance sigma squared and independence across the micro level V's, then it's elementary statistics, it's undergraduate first course statistics, that the variance of the group average error term is sigma squared over the sample size J sub I. I mean, if I just say sigma squared over N, you say, yeah, I've seen that before. This is that with J sub I as the within state sample size. And then the best linear unbiased estimator of this regression equation would be the weighted least squares estimator that applies least squares to the reweighted equation that multiplies everything through by the square root of J sub I, and hence is multiplying the sum of squares by J itself. And this raises the puzzle. It's like, well, if that's what we learned we were supposed to do to get the best precision we could, at least with a linear estimator, why did the standard errors in the columns go the opposite way from what we expected? And this is where we get to the Dickens insight, where he says, well, what if we were wrong to assume that the micro level V's were independent of each other? And at the time he said this, it was not such a familiar idea. Now everyone talks about clustering. That's what we're talking about here. What if the V's, the micro level V's within a group are correlated with each other? Most applications positively correlated. And when they're positively correlated, a simple traditional way of modeling it is with an error components model. And that was the way Dickens approached it. He said, what if the micro level V is the sum of a group level component C sub I and an idiosyncratic micro level component U sub ij, where, to make things simple, we assume the two components are independently and identically distributed with respective variances sigma c squared and sigma u squared. Of course, the reality can be more complicated, but just to get across the general point, let's take the simplest case. Well, in that case, where we have the group level error component, as you see in equation 4, the variance of the group level average, actually, maybe I should, under our previous assumptions of independence, it would look like that. The first component wouldn't be there. Okay, and we say, okay, we should reweight by the square root of J. But it adds this additional component that's unrelated to the within group sample size. So that if we do reweight, multiplying through by the square root of J, this is the variance of the error term in the equation we estimate by applying weighted least squares to the weighted data. Now, what you can see then is if the group level error component, sigma c sub squared, is substantial, and the sample size j sub I is pretty large in every group. So for example, in the divorce rate example, well, of course, it's true, California has a much bigger population than Wyoming, but there's still a lot of people in Wyoming who may or may not get divorced. Well, then the variance of the unweighted group average error term may be nearly homoscedastic. It's not exactly, but it could be that the variance for V sub I is dominated by the group component sigma c squared. The second component in equation 4 might be pretty small if j sub I is always big. Okay, so it could be that actually in the group level data, the error term was nearly homoscedastic. And that's what sort of Dickens believed was generally true. It's not always true, but he was probably right that it's often true. What if you go ahead and do the traditional weighting anyway? Well, then you actually create a heteroskedasticity issue. The variance in the next equation after equation 4, the first term, if j sub I varies a lot across states, which is the only reason to get into this weighting in the first place, you could be causing, basically if you're, let's see, which way does this go? You would be upweighting California relative to Wyoming and actually causing the reweighted California error term to have much higher variance than the Wyoming one after the weighting. Okay, so that's a possibility. I actually was a referee, you might not know this, I was a referee on an early version of the Dickens paper, and I actually was advising Econometrica to publish it. I got overruled by the editor, who at the time was Angus Eaton, but I wish they had actually. The paper would have gotten more attention had it been published there. But at that time, Bill Dickens was kind of overstating the case. The subtitle of his paper, which I think probably leads to our paper, at least subconsciously, was Why It's Never Worth Waiting. And well, that overstated. I think the version he eventually published was a little more temperate. I don't remember exactly what it was. Actually, I guess I could look it up here if I could find my bibliography fast. Oh, here we go. Oh, he changed it. He used to say why it's never worth waiting. He changed the subtitle to "Is it ever worth waiting?" I'm pretty sure the referees pushed him on that. But anyway, this provides an explanation for why weighting by the within group sample size sometimes leads to less precise estimation than OLS does, with that table of divorce rate results being a vivid example. Okay. Now, I think I've sort of noticed with, maybe especially with grad students, when they find out, ooh, actually even with the undergrads, when I taught them undergraduate econometrics, told them about heteroskedasticity, and they start getting nervous. Well, now what do I do? How do I know if this is an issue or not? And you could have that reaction and say, oh no, sometimes it's better to wait, sometimes it isn't. Now what do I do? Well, fortunately, as Dickens emphasized, it's actually easy to address this as an empirical issue because we've got all these heteroskedastic diagnostics, which people have been working out for decades. And as it happens, one of them called the modified Breusch-Pagan test, which is like mainstream enough that it actually features in Wooldridge's undergraduate econometrics textbook, turns out to be perfectly suited for testing for heteroskedasticity in this situation. And as a bonus, the results of the auxiliary regression you run in that case turns out to guide the modeling of heteroskedasticity when it appears to be present. So instead of using, in a case, I mean, some cases you say, well, OLS is probably good enough. In some cases, you'd say, well, we have some heteroskedasticity here, but it's not as extreme as the kind that used to be modeled. And you'd actually need to do an intermediate weighting. And the Breusch-Pagan test actually gives you an estimated version of the optimal weights. And the details of that are in our paper. Okay. So our first recommendation to practitioners in this situation is not to assume that heteroskedasticity is an issue or that it's not an issue, but rather to perform the appropriate diagnostics before deciding. And then, it makes me think, oh, I'm out of practice. I might have left my phone on, but I think I did remember to turn it on, surprisingly enough. Two additional recommendations. The first one is really a Wooldridge recommendation. Regardless of whether one uses weighted or unweighted estimation, in the end, if you're honest, you're going to admit, well, I don't know exactly what the behavior of the error term is. Maybe there's some heteroskedasticity remaining, however I did the weighting, and therefore there's a case for reporting heteroskedasticity robust standard errors. Jeff actually is a protege of Hal White, so of course he wants to emphasize that, as well he should. Another thing, which I think of as the Bill Dunmouchel, Greg Duncan point. Greg and I were colleagues for many years at Michigan. In a paper they published in JASA in 1983, they pointed out that it's good practice to report both the weighted and unweighted estimates, because under exogenous sampling and correct specification of the regression model for the causal effects of X on Y, both OLS and WLS should be consistent for estimating the regression coefficients. On the other hand, if you either have endogenous sampling, which we'll talk about soon, or model misspecification, that could cause a divergence in the probability limits between the two estimators. So actually, as an application of the Haussmann test, you could use the divergence between the two as a diagnostic for the combination of model misspecification and or endogenous sampling. So if you run it both ways and they come out about the same, probably most of us breathe a sigh of relief and say, oh, good, my results are robust. But many times they'll come out strikingly different. And if they're going to, it's important to know that. I mean, as we're saying, oh, let's cheer when the results are robust. But if they're not, if you get substantially different answers from OLS and WLS, something's wrong. And you as the researcher need to find out what it is. Should you believe this estimate or that one or neither of them? And in my experience, it is a pain in the butt to do the extra work to solve a puzzle, but usually it leads you to do a better research project. You end up understanding what you're studying a lot better than if you hadn't gotten smacked over the head with this indication that something's going wrong here. Okay, here's an example coming back to the specification issue a little bit. On my paper with Jin-Young Lee that I showed you that one table from, we were specifying the divorce rate in logs on, I think, the reasonable thought that, well, the divorce rate can't be negative. So we should have a corresponding functional form. And even better, would probably make more sense to do the logit, because it's really a fractional dependent variable. But for reasons I can talk with anybody about later, in this instance, because the fraction is so small and hence the denominator of the logit is so close to 1, there's almost no difference between the logit and the log. So we tried it both ways. The results were virtually identical, and what we reported in the paper was the log results. But Friedberg and Wolfers didn't log the divorce rate. They used the level of the divorce rate. But what we found in our replication work was that if you do what they did and specify in levels, the OLS and WLS estimates are dramatically different from each other, which in itself doesn't tell you what went wrong, but it makes you think about it. And, one thing I would think about right away is, well, it wasn't a very good functional form specification to begin with. It shouldn't be a linear model for the divorce rate in levels, which is a fractional dependent variable. So that's an example of using the Dunmouchel and Duncan specification test to discover something that you need to know. Okay? Well, that was actually a pretty long time to talk about, which maybe in some ways is not the most interesting case, but it matters because we work a lot with state average data, for example, or other group average data. And I think there's a tendency in the profession now to not think about heteroskedasticity much at all. Just do OLS and robustify your standard errors. But oldsters like me remember that we used to justify the weighted least squares because it could give us precision gains. And I think that's still a reason to do it. Back when I was going to a weekly empirical micro seminar, it was not my experience that the standard errors being reported were so small that we didn't have to worry about precision. It was much more typical to say, well, it's hard to know what to conclude from this research because the 95% confidence intervals are so wide. So I think driving down the standard errors is still an important thing to do when there's an easy opportunity to do it, okay? Here is maybe the most compelling reason of all for reweighting, which is very much like the story with descriptive statistics. This is when you have what I'm calling endogenous sampling. My best example comes from a classic Mansky and Lerman paper in Econometrica in '77 about choice-based sampling, as they called it. A lot of the early work on binary and discrete dependent variables was about choice of commuting mode for commuters. You know, for example, we'll simplify it, make it binary by saying the choice between driving to work or taking the bus. With a random sample of commuters, what most researchers would do would be just use maximum likelihood, estimate a probit or logit model for this binary dependent variable. But suppose the sample is drawn not as a random sample of commuters, but as a choice-based sample. And in Mansky and Lerman's words, in studying choice of mode for work trips, it is often less expensive to survey transit users at the station and auto users at the parking lot than to interview commuters at their homes. If you do the sampling that way, and you can see why people would, it's quite possible that the resulting sample will overrepresent one modal choice relative to the other compared to the population distribution of choices. And if you ignore that and maximize just the conventional probit or logit log likelihood, which in this case is an incorrect log likelihood because it fails to factor in the role of the endogenous sampling in generating the data, with rare exceptions, that's going to result in inconsistent parameter estimation. Mansky and Lerman not only noted the problem, but also had a very feasible correction for it, which was instead to maximize what I'll call the quasi-log likelihood, it takes the conventional one and just weights each observation's contribution to the log likelihood by its inverse probability of selection. So basically, it's just doing the inverse funhouse mirror again to recover representativeness of the target population. I think that's a good example, but again, it's really a much more general point, and it's covered in that 1999 Wooldridge paper for the entire class of M estimation. And the lesson is, in the presence of endogenous sampling, by which I mean sampling in which the selection probability is related to the dependent variable, even after conditioning on the explanatory variables, estimation that ignores that generally will be inconsistent. But if instead you weight your criterion function, whether it's a sum of squares or a log likelihood or whatever, by the inverse probabilities of selection, you do achieve consistency of estimation. And that's a particularly compelling situation for doing the reweight. You need to do it there, you're going to get inconsistent estimation. An additional point stressed in Wooldridge's paper and elsewhere is that if the sampling probabilities vary exogenously rather than endogenously, and they're still different across observations, but in a way that's not related to the error term in your regression, weighting is not necessary for consistency and might be harmful for precision. It could create a heteroskedasticity issue where you didn't have much of one. The example I have from my experience is I know from lots of experience that the current population survey oversamples in the less populous states. And there's a legislative history that leads to that. Actually, the Bureau of Labor Statistics was ordered to come up with unemployment rates, annual unemployment rates for every state. And they didn't have enough sample size in Wyoming to meet their own standards of precision. So they had to kick up the size of the Wyoming sample, among others. Now, so suppose you're estimating something with the CPS, but as often would be the case, it makes sense in your study to be controlling for state dummy variables. Well, in that case, you're already conditioning on the state, which is the sampling criterion that the sampling rate varies with. So if the model is correctly specified, and in practice that it's never correctly specified, right? But if it's close, is how I would approach it practically, then the error term is maybe not much related to the sampling criterion, and weighting might be unnecessary. In fact, if the error term obeys the ideal conditions, it's a theorem that OLS is optimal in the usual way. Now this asks the question, yeah, but is there any harm to doing weighted least squares? And the answer is, there can be. You could be creating heteroskedasticity, possibly to a large degree, and making your standard errors bigger. So that's an additional point to emphasize. And
Can I ask a question?
Yes,
The,
please.
Dodge's sampling. So the example you gave of commuter choice, the point of doing the choice-based sampling was because it's hard to survey people more generally. So where do you get the probability of selection numbers from? In a case,
you
like
would
that?
still need information on the relative frequencies of commuting and taking the bus.
So you combine it with some.
Yeah, it would have to be external
numbers,
data, not from your own sample, where you're asking people a lot more about, you know, how far do you live from the bus stop and how many cars do you have and all that stuff. That's what you're using the survey data because there are all these things they want to know at the micro level, but you would also need aggregate data on the relative frequencies of the two outcomes.
Okay, right.
Yeah, without that, then
Yeah.
I don't know. You don't know which weights to use. You would actually need to get that information somehow. Yes.
I'm wondering if, like, with this example you just gave of like states and that being the criterion, if would that apply also if you were using something like the PSID and you were using the panel and had like individual fixed effects? Would that also apply or no?
A good question. And it's exactly the kind of question you should be asking, this kind of think things through. And I think the answer sort of is it depends, as often it does. The question is whether controlling for the fixed effects is sufficient to get what remains in the error term to be unrelated to the sampling probability. And that kind of, it's something I've had to think about many times over. And there isn't a global answer that says you're already cool if you're controlling for the fixed effects, or you never are. It kind of mainly depends on what you're studying, whether accounting for in levels for constant effects for the individual is sufficient to it's probably close to sufficient in some cases, but you really have to think carefully about what you're estimating. And if there's certain I've advised a lot of dissertation work about earnings dynamics for workers, and there is heterogeneity among workers in their growth rates of earnings. And there's a lot of heterogeneity in levels. Someone's a high earner one year, they're probably a high earner in another year. But there's also a lot of heterogeneity in the life cycle growth rates, and fixed effects and levels don't cover that. So, I mean, not that I have anything specific to say right now about waiting for that case, but it just gets across that you have to think about what does get accounted for by fixed effects and levels and what isn't. And is it possible that what isn't is is still related to the sampling, or to the what makes the sampling rates different for different parts of the population. Okay, that might not be a very satisfying answer, but it's kind of in a way, the message of the paper for the most part is, well, think about it. But think about it in a way that recognizes what the issues are. Okay. Yes.
Thank you. So maybe to piggyback off of this question too, I've been told before, like, just control for it, like that kind of answer, and I can see that I shouldn't just do that, but I was wondering if in your ideal world, if you could like advise the paper on how they talk about the sample and the data, should we all be like much more thorough about how they sampled the data? Because I've ignored that a lot.
Yeah. And you're probably in a lot of good company, but yes, I think it's very important to know how the data are generated.
Okay.
I can give you a lot of examples in my own experience where like really spurious results in economic research that come from people, basically people running regressions that are virtually nearly identities unwittingly because they don't understand how some of their variables were constructed. But the general lesson is it's very important to know what the sample was, how the variables were defined, what imputations were done, all that stuff. It's just so easy to get things wrong if you don't know that. Let's see. I don't have much time left, do I? Yeah, anyway, most of this is just repetition. But once again, I'd say with a tip of the cap to Jeff Wooldridge, that robust standard errors are a good thing in many cases. Oh, and I'm not sure which of Jeff's papers off the top of the head, but it's probably the same 1999 one. It says, in the case of a linear regression, where you're doing the weighted estimation to account for the endogenous sampling, well, then you really need to use the white standard errors because, you know, you're differentially weighting the data, so you're surely creating a heteroskedasticity issue. But you can't not do it. You have to weight the data for consistency of the coefficient estimation. So, you know, the heteroskedasticity is just sort of an unfortunate byproduct of that, and you have to deal with it. And again, I want to make the Duncan Dumichel point that although when the variation in the sampling rate is exogenous, both the weighted and unweighted estimators are consistent, but the unweighted ones might be more precise because the weighted ones might create a big heteroskedasticity issue. But again, I want to repeat the point that you should look at both. And if they diverge a lot, that's a warning sign to you. There's something else going on that you hadn't noticed, and you better figure out what it is. Okay. And finally, we get to a motive that a lot of people, including better researchers than I am, believe to be a motive for weighting, but it was, in most cases, was actually a bit off point. Now, what we're talking about here is that something most of us realize now is that in most cases, the effects of X on Y are at least somewhat heterogeneous. Even those simple models that we estimate might proceed as if it's just one homogeneous coefficient that we're estimating. We're overlooking that aspect of reality. Now, at least the time we wrote, it was quite common for researchers to think that if they weighted their regressions by population shares, that would consistently estimate the population average of the heterogeneous effects. I knew that was wrong because I had carefully read Angus Deaton's 1997 textbook, The Analysis of Household Surveys, which I highly recommend to you. It's a wonderful book. I guess I knew to read it mostly because I knew Angus a bit, and he's one of my heroes in the profession. But what I've noticed was that what I'm going to tell you about this being a fallacy was widely known among development economists because they all read Angus's book because he was a leader in the field, and mostly not noticed much outside of development economics. As usual, we're not really making a novel contribution here. We're just kind of trying to smack our audience over the head and say, here's something you might have missed that you really need to pay attention to. So we came up with another example that kind of dovetails with the weighting issue that we're talking about. Actually, other than the weighting thing, our example is even simpler than his, but this is like proof by counterexample. We take a case where we can show you that doing this does not consistently estimate the average population effect. But I actually should mention, there's nowhere for me to write here, is it?
Yeah.
I will just say verbally, a wonderful paper for you to read if you haven't seen it already is by my young friend Timon Zloczynski, who's an assistant professor at Brandeis. He's an econometrician who writes papers that are very useful to us practitioners. And he's got a paper in Restat last year that has a much more general treatment than either Deaton or we have for the case of linear regression. And he actually shows that in a multiple regression where the variable of main interest is a dummy variable, but you have a lot of control variables, it's true that the OLS, with a representative sample, it's true that the OLS estimator of the coefficient of the dummy variable identifies a weighted average of the heterogeneous effects, but the weights are nuts. You're getting a weighted average that has nothing to do with any version of an average effect that you'd be interested in. And that's a much more general result than what I can show you. In fact, I don't know if I should even go through our example or not with limited time. Any advice on that?
I think that people, I think this is the main thing, right?
It's an important thing. Okay, let's go for
We've
it.
got like 10 minutes, 10-ish.
Okay.
You think you would have time?
Yeah. And it's such a simple example that by design. So suppose the true data generating process here is y depends on x. It also depends on the dummy variable d, which is an indicator for urban versus rural, and the interaction of the two. The point of having the interaction here is to give you a simple example of heterogeneous effects. So the effect of x on y in the urban sector is beta 2 plus beta 4. The interaction coefficient kicks in. In the rural sector, it's only beta 2. So then the weighted average for the population is beta 2 plus pi times beta 4, where pi is the urban share of the population. So it's like the simplest example we can give you of a heterogeneous effect. Now, suppose you don't know that the effect's heterogeneous, or else you just ignore it, and you do a regression of y on x and d without the interaction term, hence assuming homogeneity of the effect of x. And suppose you do that with data from a survey that oversampled, say, in the urban sector, so that the urban fraction of the sample is p, which is greater than pi. The OLS estimator of the coefficient x does identify a weighted average of the rural and urban effects, but you wouldn't expect it to be the population average. Why would it be? Your sample is unrepresentative with respect to urban versus rural. And that's one of the reasons why OLS is not consistent for the population average partial effect. But actually, there's a second reason, which is that in least squares estimation, the influence of observations on the least squares estimator vary with how extreme the values of the explanatory variables are. Sometimes the language of leverage points is used for that. As a result, the weighted average of the rural and urban effects identified by OLS depends not only on the sample shares of the two sectors, but also on how the within sector variance of X differs between the two sectors. Okay. And as a result, weighting to get the sample to downweight the urban part and upweight the rural part, so they're kind of in balance with the population shares, solves the first source of inconsistency, but doesn't address the second one. And the math's in the paper, but the bottom line is that neither the OLS estimator nor the WLS estimator, they both identify weighted averages of the heterogeneous effects, and they're different ones, but neither one identifies the population average effect in general. So, well, we won't do the math here, but you can look it up in the paper. It was so simple, even I could do it. It's pretty obvious results. So the lessons are, do not fall prey to the fallacy that least squares, well, either with a representative sample or with reweighting an unrepresentative sample to make it representative, actually identifies the population average partial effect. Which, if that surprises you, maybe I should point out, it actually does identify the linear population projection, but that's not the same thing as the average partial effect. And I think I first understood that when I read Deaton's example. Again, this especially underscores the usefulness of doing it both ways and seeing if there's a divergence between the two. I said before, the Dumichel-Duncan version of the Haussmann test can serve as a test for misspecification. And this is an example. This is where you fail to specify the heterogeneity of the effects. And now I get to, actually, I do want to talk about this. This is a part of the paper I'm proudest of upon rereading it years later, because I feel like we were ahead of our time. We were still ahead of our time on this. A lot of smart folks these days, including Martha's and my dear friend, Andrew Goodman Bacon, are writing papers about how to tweak least squares estimation so that you do identify the average partial effect. And this is good work. I don't mean to say forget all that, but I also think it's overly narrow, because in most cases I can think of, the average partial effect is not the only thing we want to know if there are heterogeneous effects. So our advice is, if there is substantial heterogeneity of effects, you should study that as part of your project. And one way we make that case is to point out that unless one understands the heterogeneity, it's probably not going to be possible for you to extrapolate even a well-estimated population average effect in your setting to what it would be in a different setting. Now, in the very simple example I gave you with the urban-rural difference, the solution is very simple, which is when you run the regression, include the interaction term instead of omitting it. Of course, in practice, things could get somewhat more complicated, but at least as long as the heterogeneity is related to observables, it's something you could study in various ways. And something that's really probably just sort of a generalization of throwing in the one interaction term. And we strongly advise that. Okay, so I can summarize now. So we started off by saying, let's kind of bifurcate the question of what are we trying to estimate into two types, descriptive statistics and estimation of causal effects. In the former case, weighting's called for when it's needed to make the analysis sample representative of the target population. And the survey statisticians have known that probably for about as long as there have been survey statisticians. But on the matter of identifying causal effects, the matter is more nuanced. And we focused on three pretty commonly occurring potential motives for weighting. The heteroskedasticity one, which comes up especially with a special force when you're using group average data with group sample sizes that are very different from each other. Also to achieve consistent estimation with endogenous sampling. And this sort of mythical one of imagining that you identify average partial effects in the presence of unmodeled heterogeneity of effects. So mainly what we've said in each case is we've noticed that there's stuff to think about for each of these three. And at some points, we've noted instances in which weighting is not as good an idea as researchers often have presumed it to be. So our overall message is to take seriously the question in our title, what are we waiting for? be clear about the reason that you're thinking about weighting. Carefully about whether the reason really applies, and where there's conceptually some ambiguity, like in the case Dickens analyzed with the group average data, avail yourself of the appropriate diagnostics. And then two other themes that kept coming up was it's probably a good idea whenever weighting might be a good idea to report both the weighting and unweighted estimates, to give the data a chance to whack you over the head with a surprising divergence in the results, which would force you to think more deeply about why did they come out different? What am I missing? And in the end, you'll probably learn a lot and write a better paper if you have to confront that. And then with due respect to Jeff Woolridge and Hal White, also in many of the situations we've discussed, it's a good idea to use robust standard errors. Oh, what else have you got?
So I think we have time for a few questions, if you're willing to take them, Jerry.
Of course I am.
Good. Well, if there are no questions, then there's one that I have. It's on the button.
I'm having trouble hearing you, partly because my hearing's so good.
So I think, I guess I've heard of some possible diagnostic approaches for kind of assessing, I think statistics mentioned this, but assessing the amount of heterogeneity and how much that affects the end. What do you think about those kind of?
I'm probably less up to date on that than you are. But in general principle, seems like a good idea. And the simple example I was giving, that was basically mean eyeballing the estimated coefficient of the interaction. If it's very small, you might just say, why even bother with it? It's close enough to homogeneity. For just the sake of parsimony, maybe I'll just stick to the version of the model with without the interaction. Although you probably have a column of results that says, well, here's you can see what happens if I have the interaction term. But actually, that's sort of I'm pretty, general, I'm inclined to keep things simple as possible. Right, say check for the heterogeneity. Not that big of a deal. Tell the reader why you believe it's not that big of a deal. Let's stick to the simpler model. But of course, you don't know unless you check. So yeah, it's important for whatever is feasible for what you're estimating and where the heterogeneity might be, to have a look and see if it's an issue. I mean, it's probably always an issue, at least a little bit. The question is it enough of an issue that you really need to attend to it? And that's actually a much more general point. And probably usually if there's a time series aspect to your data, you probably have at least somewhat of a serial correlation issue. But if it hardly amounts to anything, why bother? And actually, I've been saying this for years about clustering. When Colin Cameron sent me a draft of one of his papers, they're saying, well, you talk about all these things, complicated things to do for correcting for multidimensional clustering. I said, why aren't you advising your readers to check for it first? And it's not that hard. You can start with OLS residuals, you can calculate what the so-called intra-class correlation coefficients are within the cluster. And if they're really small, maybe you could just keep things simple and not get into all that stuff. On the other hand, you want to give the data a chance to alert you that this is a big issue and you need to attend to it. So that's right, more of an answer than you were looking for.
No,
but I think it's actually much more general than your question. It's always a good idea to keep looking for things that might matter. But my approach usually, maybe just because I'm not really all that technically adept. And also I'm worried about the more complicated the model is, the more likely we'll make computing errors. Gives you lots of horror stories about that. I like to keep it simple when it's possible, for a lot of reasons, including just to make things easier for the reader. It's, lots of people are very much on the other side of that, so that's just my idiosyncratic approach. Other questions or thoughts?
Well, I think we have to let people go
Yeah.
soon because they've got to commute, many of them. So let's think theory.